Hey, I'm going to talk about the chain rule using intermediate variables or functions. Sometimes we think about these as parametric functions. Over on the left here we have a multivariable function, w equals z minus the sine of xy. So it has three inputs and one output, but what makes it more interesting is that x is a function of t, x equals t. Y is a function of t, y equals the natural log of t, and z equals e to the t minus 1. So w is a function of x, y, z, while x, y, z are functions of t. And our goal here is going to be to find the derivative of w with respect to t. Okay, so w is written in terms of x, y, and z, but we want the derivative with respect to t, because t is really the underlying decider of how this thing behaves. Now, one option is you could take the expressions for x, y, and z, plug them in, and have w completely in terms of t. How useful that is really depends on the function, but sometimes the way things are written, when you can't make that substitution as far as an abstract form, you definitely need to be able to talk about a chain rule where we go from one function to another. So I have that written out, the formula for it up here. And basically, we're going to take the partial of every function we have here, of the partial with respect to x, the partial with respect to y, the partial with respect to z. But that just gives us the functions in terms of x, y, and z. And then we have to tack on, kind of like a chain rule, the derivative of x. So then we have a partial with respect to t of x, partial of y with respect to t, and a partial of z with respect to t. So this is kind of like the regular chain rule, where in here might be u, and the derivative of u pops out. So since we're taking a derivative of w, that will happen. But since w is centered around x, we have to take the derivative of x. And since it's a function of t, just like in the regular chain rule, it kind of pops out that extra multiplier. So let's see if we can do it with this particular function. Try to pick some simple ones so they won't overwhelm us, and we may not clean it up at all. But the partial of w with respect to x. Well, z goes away. Negative sine would be a negative cosine of xy. And the derivative of xy with respect to x would be y. And then the partial of x with respect to t would be 1. So keeping in mind with what we've got here, here is the wx, and here is the xt, if that helps. So then we need a partial of w with respect to y, which will look very similar. It will look like negative cosine of xy times x, this is with respect to y. The x is the constant. Then the derivative of y, derivative of natural log of t, is 1 over t. So making sure you see where things come from. Here is the w with respect to y. And here is the y with respect to t. Okay, and then the last part to tack on is w with respect to z. Well, z is by itself, so that gives us 1, and then the whole sine function over there disappears since it doesn't have a z in it. And then the derivative of z with respect to t, e to the t minus 1, will give us e to the t minus 1. So here is wz, and the part that gets tacked on is the zt partial. I guess we could clean that up. We might as well. We've got the time. So we get negative y cosine of xy. And then we get minus x over t cosine of xy. And then plus e to the t minus 1. So now this thing is in terms of x, y, could be z, but there's no z there, and t. So we kind of have to know a whole lot of things, but we do have the derivative with respect to t. If we wanted to, we could go back and we could place x and y now if we want to. I don't see much advantage in doing that though. Okay. I don't know if that seemed like a lot to keep up with, but let me show you a variation of that. My diagram is not the most aesthetic, but over here I have a set of functions. Once again, w is in terms of x, y, and z. This time is in terms of u and v. So there's two underlying variables, and we're going to find the partial of w with respect to u. So since w is a more than one variable, we're going to have to treat that as, I'm going to pull this down so you can see my writing over here. We might push it up or move me in a second. Let's move me. Here, I'll go hide down here in the corner. But since w is in terms of two variables underlying u and v, we don't really have a good chance of figuring out how w changes just with u. So it's a partial. Well, that might make the partial notation seem a little bit better. But over here, I have, once again, the same layout we used for the partial of w with respect to t, except now it's respect to u using that chain rule. Have the variation here where we're taking the partial of w. We take the partial of w with respect to x, and then we multiply that by the partial of x with respect to u. And then we'll add to it the y component and the corresponding u component for y. And we also have partial with respect to z, and then the partial of z with respect to u. So we have the whole thing here, so if we kind of connect it, we're just kind of bringing down each little section. Okay. So this diagram is just a way that kind of helps you keep track of things if you don't have the formula in front of you, especially if you had many variables involved. So it doesn't have to be just a function of 3 variables and a function of 2 variables. But this is where we're at. So let's see here. So the partial of w with respect to u. We've already talked about how my partial notation is not super neat. It still looks like a 2. Let's drag it down. Anyway, I still don't like it. One more attempt at making that look right. It's better than usual. Okay, so w with respect to x, we get y, and that's it. So let's don't overdo that. We get y, and then x with respect to u is 1, and then w with respect to y is x plus z. Yeah. And then y with respect to u is 1. And then w with respect to z would be y plus x. And then z with respect to u would be v. So let's clean up a little bit. How much is not super necessary, but we get y plus x plus z plus yv plus xv. And once again, we talked about if we had something to plug in. If we were just given a u and a v, we could plug those in, but we might also have to come back and use those in the parametric formulas to calculate x, y, and z to plug in. But we have all the information that if we're given something, we can come back and calculate all the necessary parts. So basically this is the chain rule because one function is defined in terms of another, and when you take the derivative of that function, you have to tack on the derivative of the composite function there.